Okay. In linear algebra, you have basically two complementary concepts. One is linear combinations. So linear combination is like the operation that allows you to like create a set of vectors. Okay. If you have two vectors, you take the linear combination, you get a plane, right? And you have another vector outside this plane, you get the whole area, right? So linear combination is like the operation that you can like generate stuff, right? You generate a lot of stuff. Okay. What we focus now is the condition that allows you to ensure that the vectors that you add to generate stuff, they are all necessary. You don't have too many vectors. Okay. And it talks about the set of vectors that sort of like are necessary to create stuff. Okay. You don't want too many vectors. Okay. Okay. So let me give you. Let me start by some example. Okay. So a quick review: linear combinations again. Okay. Span, set of all linear combinations. You should be familiar with this already. Okay. But I'll talk about it every lectures. Okay. So don't get mad. Okay. Okay. So let me skip some of the lemmas. I'll come back and prove some of this later on. Okay. All right. So okay. Now, so suppose I have two vectors, and these two vectors generate. If you take this its span, you have a plane like that. Okay. Now, if I have another vector already on the plane, okay, adding this vector into the, so I have vector v1, call it u, and this vector v, and this is w. Okay, I have u and v. I can create this plane. Okay. Now I pick another vector w belonging to this plane as well. Do we need to add w to the set to create the plane? Is w needed for the plane? No. Okay. So I want some condition to prevent me from having w. Okay. You think of this as we have a set of vectors that we have a set of vectors. The span of this set of vectors is some vector space, but this set of vector has some other vector that I can remove. Okay, because they are not necessary. Okay, like for this example, if I have this set of vectors u, v, and w, I can say like w is not necessary because, you know, leaving it out, you still have the same span. Okay, we need some formal way or some precise definition to say, okay, I don't need you. Okay, okay, you are like useless. Okay, you don't want to be useless, but sometimes you're useless. We can kill it. Okay, basically. Okay, so so let's look back. Okay, so you have a set of vector like this. If you have vector u1, u2 up to un, and I take the span of u1 up to un. Okay, so this is my first set. I want to be able to say like, okay, if un is something, I can say that this span equals the span of u1 up to un minus 1. Okay, that is un is not needed. Okay. Okay. What should this condition be? Okay, so this is what we learned now. Okay, so we want to be able to say, okay, if UN is something, okay, we can just kick it out, and it doesn't really hurt us at all. So why is this thing useful? Why is this thing meaningful, or is something relevant to us? Okay. Before we gonna see some definition and example, let me give you one more example. Okay, so suppose we have these equations. So suppose we have three variables. We have equation say x1 plus x2 plus x3 equals 0. Let's say equals something else, 10. Let's do with 0 first. And then I also have this equation 2x1 plus 3x2 plus 5x3 equals 0. Okay. Suppose I only have one equation. Suppose I only have the first equations. By having another equations, I sort of like give more constraint to my solutions. Okay. If I only have one solution, one equations, the set of solution will look like a plane, right? If I have this equation as well, the set of the possible solution to the first equation is a plane, and also the set of possible solution to this is also another plane, and the intersection is a line. Okay. So by having two equations, I change the set of solutions that are possible. Okay. But if I add another equation that look like this, suppose I add the solution that look like x1 plus 2x2 plus 4x3 equals 0. Does this change anything? So what is this equation? It's basically the second equation minus the first equation, right? So adding these equations doesn't change anything. Okay. If I feel like funny, I could also add these equations x2 plus 3x3 equals 0. Does it change anything? You can see that let's call this the first equation, this second equation. This one, the third equation, is basically second equation minus the first, right? And the fourth equation is basically what is it? This second minus 2 times, right? So this equation and this equation is like sort of like useless to our problem, right? We don't need it. Okay, it's there. It's okay. It's okay to have it, but it's just some unnecessary complications that we need to deal with, right? So we don't need it. Okay. So we need a way to say that some vector is like that. It's useless. Okay? Because we want to do that because we really wanted to get only the necessary thing, the essence of the vector space that we are looking at. Okay? We don't want, some useless vectors. Okay? So can be removed, right? Okay, so can you explain why we don't need these equations? Because we can derive it from something that we already know, right? If we know that the first equation is true and the second equation is true, this can be derived. It's a product. I don't want to use a product, but because product is like multiplications, but it's a result of you can derive it from the other equations. This equation as well, right? So it's the same kind of thing as this vector W. Okay. If you want to generate this plane, I only need two vectors. Adding the third vector is like doesn't help at all because the third vector can be generated using the first two vectors. Okay? So when we have the issue like that, okay, when we have a set of vectors where some of the vector can be removed, we say that this set of vectors are not linearly independent. Okay, the concept of linear independence is like everything that you have is not a linear combination of the other thing. Okay, so that's they are independent. Like these three vectors are not linearly independent because some of the vector can be expressed as a linear combination of the other two. Also this one, if you take these four equations, in a way these four equations are not linearly independent because the last two equations is basically can be derived from the first two. Okay. All right. So people don't say that equations are linearly independent. I use it in the wrong sense of word, but when you just look at the coefficient vectors, they are not linearly independent. Okay. Okay. So let's see the definition. So we say that vectors u1 up to un are linearly independent if no vector can be written as a linear combination of the other vectors. That is, you cannot create any of the vectors out of the rest. Okay, you cannot say, okay, this second vector can be is a linear combination of other vectors, so it can be created from the other vectors. So that set is not linearly independent. Okay, linearly independent is like, you don't have anything that are not needed. Okay. The other way for the first one is like the first definition is not that useful when you want to prove stuff. This is another definition which is equivalent. So we say that vectors u1 up to un are linearly independent if the only solution of this equation is this. So you have equation like you want to add them up. So the only linear combination of these vectors, this n vectors that become 0 are the case when you take none of them. Okay, so this is a linear combination, but this is a linear combination where every coefficient is 0. So the only way you can get to 0, okay, is that you take none of them. You take none of the vectors. So let's see this graphically. Okay. So if I have these two vectors, then look at the case in two-dimensional space. If I have these vectors and that vectors, can I find a linear combination of these two vectors that go to 0? I have u, vector u, and I have vector v. Okay. The only way I can get to 0 is like, it's basically I take 0 unit of u and 0 unit of v, right? There's no other way. Okay. But if I add another vector w, say this one, can I find a linear combination of these three vectors that go to 0? One possible way is like I take none of them, right? But I can do this. I can also do this. I take w and then I take. Okay. I can add w with some minus v minus u. This is minus u, right? Minus maybe 1.5 u, and then I add v. So this is alpha 1 u. This is alpha 2 v. And I get back to 0. Okay. In this case, you can see that if I have these three vectors w, u, and v, okay, I can have some coefficients. I can have a linear combination that of these three vectors to get to 0 without where some of them is non-zero. Okay. So in this case, these three vectors are not linearly independent. Okay, you have a set of vectors are linearly independent if the only way you can get to 0 is by taking none of them. But if you can combine them somehow to get to 0 vectors, okay, that means there are some vectors that can be rewritten as a linear combination of the others. Like for this one, W, right? If you have non-zero W, it means like the other vector can move you back to 0, right? So it means some of them can be combined to get to W. So W can be rewritten as a linear combination of the other vectors. So that's not linearly independent. Okay? So the concept of linearly independence is like not that easy, okay, to understand, but you should try to be familiar with it, okay? แบบฝึกหัดครับ you take the exercise U1 and U2 is this set linearly independent? Why is this set linearly independent? So you have two vectors, right? So if these two vectors are not linearly independent, it means like you can write U2 as a linear combination of U1, right? But U2 cannot be written as a linear combination of U1 because what? Can you write U2 as a linear as some scaling of V1? Can you scale V1 U1 to get U2? No. Why? So you can say that the third. So basically, you cannot scale 0 to get 1, right? You have nothing. Like you have a drink that contains no sugar at all. Okay, and this one is a drink with 1 unit of sugar. You cannot eat. You cannot, how many bottles of the first type of drink? You cannot get any sugar. So it's impossible to get U2. So U1 and U2 are. So U2 is not a linear combination of U1. So this set is linearly independent. Okay. Now find other vectors U3. So this is one way to write it down. Okay. But you can use the definition, the second definition that we have. So the other definition of linearly independence is the following. You can also use the other definition that we have. These definitions. Okay. If you want to use these definitions, you want to say that the only solution of this equation is when all the coefficient is 0. Okay. So let me show you how to use this definition. Okay. If you want to use that definition, we can say this. Let me write here. Consider equation alpha 1 U1 plus alpha 2 U2 equals 0. Okay. But this is like alpha 1 U1 is 1 1 0 plus alpha 2 0 1 1 equals 0. Since the last, you can just conclude, right? So this means this will be true if it's true when the first coordinate, right? So alpha 1 times 1 plus 0 alpha 2 equals 0, right? So alpha 1 times 1 plus alpha 2 times 0 equals 0, and the last coordinate, right? So alpha 1 times 0 plus alpha 2 times 1 equals 0, and this implies that alpha 1 equals alpha 2 equals 0. So the only way you can get this equation to be 0 is when the coefficients are all 0. Okay. So in that case, we say that U1 and U2 are linearly independent. Okay. So if you use this definition, it's more cleaner, but it doesn't really make any sense if you don't understand the definition. Okay. But the idea is like you cannot combine the first two vectors to get to 0 without taking none of them. Okay, so this one, for a vector u such that u does not belong to this span, come up with some vectors, some numbers. So let me give you a solution that is not incorrect. It's not correct. So if I pick this one vectors, is this vector belong to the span u1, u2? Yes. So if I answer this, then I 0. Okay. If I pick 1, 3, 2, what do you get? Okay. Pick something that do not belong to span u1, u2. Can I pick 0, 0, 0? Does it belong to the span of u1, u2? Yes, because 0 vector belongs to whatever span you take, right? So, okay, pick one, okay, and then try to argue that this set of vectors are linearly independent. Okay. 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 There are a few possible answers. This one is also good. This one is not, okay, because you can just take this and minus that, right? Subtract that. And you can also, this one, I think this one is also good. This one is also good, okay? Okay. A lot of possible answers, okay? If you just pick some random vectors, it's unlikely that you belong to this span, so you have to be really unlucky about that, okay? So is this set linearly independent? Yes, because you can argue that because u2 is not linear, is not a linear combination of u1, and also u3 is not a linear combination of u1 and u2 because it does not belong to the span of u1 and u2. So this 3 vector cannot be written as a linear combination of the other vectors. So this set of vector is linearly independent. Okay. But mathematically, if you would like to check if a vector is are linearly independent, you can check this with this condition. Okay. But these conditions this is a vector's equations, but you can write it as a linear system. So let me do that really quickly, so that because we don't have that much time. So you wanna check if so you have these 3 vectors and you have 3 variables. These 3 variables, okay. You wanna write an equation for these 3 variables, okay. So how can we write that? Okay, so it's basically this equations. So you have alpha 1 times u1, so u1 is 1, 2, 4, right? And then alpha 2 times u2, 2, 0, 4, 2, and alpha 3 times 2, 2, 3, 3. And I want this all to be 0. Right. So how can I write them as a linear system? So I will have a linear system with 4 equations and 3 variables. How can I write that? So you can look at the first coordinate. Okay, the first coordinate. Okay. If you look at the first row, it says alpha 1. 1 times alpha 1 plus 2 times alpha 2 plus 2 times alpha 3 equals 0. That's the first equation. The second equation corresponds to the second rows. What does it say? 2 times alpha 1, right? 2 times alpha 1 plus 0 times alpha 2, I can just ignore it, and then 2 times alpha 3 equals 0. This is the second equation. The third equation says
4 alpha 2 plus 3 alpha 3 equals 0. And finally, the last equation say 4 alpha 1 plus 3 alpha 3 equals 0. So this is the linear system I'm talking about.
Okay, when we talk about system, it's like you have many equations. That's it. When you see systems, like okay, many equations. That's it. So a linear system is like a set of linear equations. So you have 3 variables and 4 equations. If these 3 vectors are linearly independent, the only way you can satisfy all 4 equations is to set all these 3 variables to be 0. Okay? For which I think you need to do that. That's the only way, I think. But this question doesn't ask you to solve it. This question asks you to write down these equations. So we will come back on Thursday regarding this kind of linear system. For today, I think we kind of run out. Okay, so let me conclude real quick. Okay, today we review the concept of what we did linear combinations. And if you have a set vector and takes all the linear combination of that vectors, we get a span. So a span is like you have a vector and you generate a bunch of vectors. Okay. The other concept that we cover today is linear independent. Linear independent talks about a set of vectors that are necessary to create the set of span. Okay. It's like you don't have extra vectors. You only have the required vectors to create a span. Okay? We'll come back on that on Thursday. Okay, good luck. Thank you.